Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 2 of the lecture on Monte Carlo simulation. So here on our outline, we're on the theory of Monte Carlo simulation. So I had described one description of Monte Carlo simulation is a method for computing a function of a random variable and doing it by replacing that random variable with a large sample of values from its distribution, right? So I'm going to go ahead and walk through that approach. So the basic idea, right? We're interested in some variable y, and I'm going to say that y is equal to flood damage. And y is a complex function of some variable x, and I'm going to say x is equal to flow. Right? So we're saying y is some complex function of x. Okay, x is a random variable that is described by some probability distribution. So here's my distribution of x over here. I'm showing a normal distribution, but this is general. It could be any distribution. So x is a random variable, and therefore y, which is a function of x, also must be a random variable with a probability distribution. If we're interested in the distribution of y, we can determine it analytically, and that would require taking this equation of the probability distribution and routing it through this complex function of x, right? And probability distribution functions are often quite ugly, especially the normal distribution, but a lot of them are hard to work with. And so it's not appealing to me to take a probability distribution equation through any kind of function. And so my preference is going to be, let's determine the distribution of y using Monte Carlo simulation, right? So what we're going to do is we're going to replace the probability distribution of random variable x with a large sample of random values from it, right? So if this is the distribution of x, this histogram represents my large sample of values from x, right? And the histogram is doing a nice job of replacing that PDF of x, right? Because we have a large enough sample. Right now, for each member of the sample of x, I'm going to compute this function y equals some function of x, right? So for every sample member, I'm computing damage y, right? So this process is going to create a large sample of y. Right, here's my large sample of y, of damages. And from that large sample, I can infer the probability distribution of y with the same methods that we're learning in this class this week. Right, so now based on my probability distribution of x and the function of y given x, I have a distribution of y. Now, an important thing to note is that Monte Carlo simulation does not add any information to our analysis. All it does is integrate the random variables with the specified probability distributions. So we did have some data at one point in this process. I'm going to back up. Hopefully, I'm going to back up. It's taking a little while to back up. There we are, I've backed up. Okay, so to estimate this original probability distribution of x, I had some data and estimated that distribution. But then that distribution I've chosen for x is the input to the Monte Carlo, not the original data that led me to estimate it, right? Then in the next step, where I've generated this sample of x, this is just random values created just to flesh out this distribution. So if I have large values of x, large flows, up in this upper tail, and thus I have large damages. These values didn't happen. This isn't data. This is just values that were chosen to flesh out this distribution, right? So the Monte Carlo is based only on the distribution of x, and not the data that originally let me estimate a distribution for x, and any of the values that I evaluate in the Monte Carlo simulation are also not data, right? They're just values that allowed me to do the computation. Right, this is very important to note. No information is added by Monte Carlo. Right, so I mentioned earlier that we could use any number of input variables with no added complexity. Right, so let's add another one. So we have our random variable y is damage, and it's a function of, in this case, two random variables, x and z. Right, let's say x is still flow and z is the starting level of a reservoir upstream. Right, so different levels of the reservoir at the start of a flood event are going to give us different releases from the reservoir because there's different space to store the flood. Right, so in this case, we're going to create a sample of random variable x, a sample of flows. We're going to create a sample of variable z, the reservoir level. And then we're going to take one value from each sample and compute damage as a function of those two values. right? And for every member of X and Z, I'm going to compute damage. And so I'm still going to end up with a large sample of damages of variable Y, right? So the process is the same. I just had to create samples of two variables. Now, in this case, I created independent samples of X and Z. I assume they were unrelated. If X and Z are correlated, and we're going to talk about correlation a little bit later as we get into multivariate probability distributions, but it just means that they vary together in some way or are related to some degree. And so if they are correlated, we can use correlated random sampling to maintain that relationship, right? So we can also do this process with dependent or conditional random variables, right? Maybe the reservoir is kept at different levels at different times of the year, and so the season matters, and the likelihood of flood event flow is going to vary by the season as well. So maybe we create a random sample of season first, right? Select for each member of the sample of season, we're then going to sample our flow and our starting storage for that event from conditional distributions based on season, right? So then we're going to create a sample member of X for X given season, and we're going to create a sample member of Z for Z given season, right? And then still from every one member from each sample, we're going to compute damage given flow, season, and reservoir level, right? We're still going to end up with a large sample of damage Y. Okay, so this is called two-stage sampling, and really we can have any stage of sampling. Any variable can be based on any other earlier random variable with a conditional distribution. Okay. So what about generating the random sample? How do we do that? Well, we saw it in the introductory lecture. We're going to go through it, though, in a little bit more detail. Right, the first thing we need to do is switch from the PDF form to the CDF form, and I'm starting this time with a normal distribution again, but it is general. It'll work for any distribution. So here's our CDF form. Now we're going to generate random values that are uniformly distributed between 0 and 1. Random number generators generally do produce pseudo-random numbers like this between 0 and 1. Right, I'm going to use those uniform values as a cumulative probability, right, and compute the inverse CDF. Now, I like to look at this more visually. So I'm going to put my uniform 0 to 1 value on the vertical axis, and I'm going to shoot it through the CDF and down, and that's going to give me a value from my distribution. Right, then I'm going to take another uniform value and shoot it through and get another value of X, and then another, and another, and another, and another. So with each uniform 0 to 1 random value, I get a value of X. Now, even though by definition the values along this axis, the vertical axis, are going to be uniform, the values aren't going to be uniform along the x-axis. Right? They're going to be distributed based on the shape of the CDF. So here, where the CDF is steep, a wide range of the probability axis is going to create a narrower range of X. And here, down here, and up here, where the CDF is much more shallow sloped, then a narrow range of probability is going to give me a wide range of X, right? So the result of that is going to be my X's clustered, more of them in the center and fewer of them out in the tails. And then if you can imagine doing a histogram of those values, it's going to be shaped with more in the middle and fewer out on the tails, like my original distribution, right? So this is how we're going to generate a sample that matches the PDF that we started with, right? Now, I like to view it as the reflecting values through the curve, but mathematically, it's just saying that the uniformly distributed random value U is the cumulative distribution function. And then we solve for X using the inverse CDF. That's also called the quantile function. If you think back to the introductory lecture, this is exactly what we did with a CDF for a six-sided die, right? So this step function here is the CDF for the six-sided die, where I divided my probability range into 6 even parts, and then for each uniformly distributed random value, I reflected through and down. And in this case, we just get piles of values at each integer 1 through 6. Right? And obviously I do a lot more than these, and I'll get a big, probably, hopefully even pile of values at each of these integers 1 through 6. Right, so that's what it looked like to what we did in the introductory lecture. Right, so what about how large a sample of values we need? Right, so what we are looking for is a representative sample, and a sample is large enough to be representative if we can produce the correct distribution parameters from the sample estimators. Right, accuracy increases as the sample size increases, meaning a random sample becomes bigger. Meaning a random sample becomes more representative as it gets larger. A non-random sample doesn't necessarily become more representative, but a random sample is going to be more representative as it gets larger. Right, so let's do a quick experiment generating a random sample from a standard normal distribution and see what that looks like. Right, so the standard normal distribution, if you recall, has a mean of 0 and a standard deviation of 1. If we create a sample of size 25, here's a column of 25 uniformly distributed random values between 0 and 1. They're each reflected through the standard normal CDF and down, so my value of 0.412 comes across and down to a little less than 0, or minus 0.2. My high value here of 0.924 comes over and down to about 1.5. Right, so these blue dots are my other 23 uniformly distributed random values put on this axis, reflected through and down. Right, so this second column is my 25 standard normal values. So here we have this block here is creating the histogram, which I'm showing here in red in front of the input distribution of standard normal. Down here, I've got my computed sample statistics, mean, standard deviation, and also skew. So my mean is minus 0.04. My standard deviation is 0.74, and my skew is 0.78. So I expected my mean to be 0. I expected my standard deviation to be 1. And I didn't mention it for the normal distribution, but the skew for the normal distribution is 0. Right? It doesn't even have skew as a parameter, but the skew is 0 because it's symmetrical. So having a skew of 0.78, which is happening because we have more values on the high side here. Obviously, these plus the shape of the histogram itself is enough to show us that a sample of size 25 is not adequate to replace this probability distribution. Right, so 25 is too small. Let's look at some bigger samples. Right, so here we have a sample of 100, a sample of 1,000, and a sample of 10,000. Okay, now with only 100, we're probably going to figure out the middle of the distribution pretty well. The central tendency is going to be pretty accurate. Right, we'll get an idea of the spread. With a sample of 1,000, I'm doing pretty well on the spread, and I'm starting to fill in the tails of the distribution here and here. With a sample of 10,000, now I'm starting to do a good job in these tails. Right, so how big of a sample do we need? Well, it depends on what we need to know about our output. Right, so we can say the input sample is large enough when it adequately reproduces the input probability distribution, but let's look at it instead from the perspective of the output sample. Right, the output sample is big enough when the statistics of interest stabilize, meaning the statistics stop changing with each new sample member within some delta. Okay, that's known as convergence. So this implies, though, that we're not just going to create a sample and then work forward. It implies that we're going to create a sample one member at a time, do my analysis on the sample member, recompute my output statistics with that sample member before moving on. Right. Quick note, what's the relationship between the input sample and the output sample? They are the same. Right. We're looking at the question from the perspective of the output sample. So we're going to be computing our sample now one member at a time. We continue creating and evaluating new sample members until the statistic of interest stabilizes. Right? So if this is my output distribution here, maybe I'm interested in the average, maybe I'm interested in some value in the upper tail, like a 1% value. So depending on which one I'm looking at will affect what sample size I need. Right, so here is a sample with 100 members, and computing the average of these damages, it does stabilize fairly well with the 100 sample members. But if I was interested in that 1% value, if I compute my 1% exceedance value as I accumulate sample members, it is definitely not stabilized. And it's not surprising that a 1 in 100 value is not going to stabilize yet with only 100 sample members. But if I repeat with 1,000 sample members, then I'm seeing that the 1% value does stabilize. And whether or not it is stabilized within delta depends on what we choose for delta, which means how strict of a convergence criteria we've specified. Right? But we can see, though, that we need a much larger sample if we're interested in the upper tail rather than the average. That's the end of the second video. This shows that we would be doing the workshop next if we were in person, but in fact, video 3 is going to be on the applications. And so I will see you in video 3.